We have another co-moderator from NCK, and we have Dr. Lauren, Dr. Peter, and from NTU, Professor Chen, and Mr. Zhou from the utility company, Mr. Sui. Good afternoon, everyone. First of all, it is with great delight that I serve as the co-moderator of this session. And our topic is digital development in the water sector. In the water sector, play the frontline work in this sector. The introduction of technology is rapidly being deployed. And you probably all attended the summit this morning. At the summit, we heard about challenges in the sector and how we can leverage AI technologies to help us face challenges such as climate change and social challenges. And this way, we have improved ways to tackle these problems. Today, we are very honored to have from the industry, academia, and the government, local and international, to help us share some experiences and practice, including digital twin, IoT, and other high-tech technologies that can be leveraged in our practice. I'm sure you will learn a lot from the upcoming presentations. Once again, I want to thank all of you for taking part, and I wish today's forum success. I wish you health. Thank you. Now, without further ado, let's go right into our presentations today. Now, I would like to invite VP from Taiwan Water of Taiwan Water, Mr. Wu. I used to work very close with him. With his assistance, we are able to meet the high demand from the high-tech industry. He comes with extensive experience in water planning and practices. Now he's going to speak with us about the AI application at Taiwan Water with the neural network and dynamic water supply. The two co-moderators, Secretary General from WRA, Professor Dong, distinguished guests, ladies and gentlemen, good afternoon. I am Wu Jingwen from Taiwan Water Corporation. Today, the topic I'm going to share with you is the neural network dynamic water supply information, AI applications at Taiwan Water. To your right, you see this graph. This is our vision for water supply in the future. There is still currently some gap, and there are some room for improvement and optimization, but it is a clear goal. At Taiwan Water, we are firmly on our way toward AI. This graph I got from Microsoft and Tyler. It took me a few minutes to get this drawn. It's includes the human body, include the vascular, the blood vessels, the neurons, and various components. The human body is a very precise and complex system. From AI, we can learn the total length of the human muscles, including the arteries, veins. The total is 60,000 kilometers, enough to circumscribe the Earth by twice. And our heart every day pumps fresh oxygen through the artery across the whole body, whereas the veins take away the carbon dioxide back to the heart. And also we have the micro vessels in bringing oxygen and nutrients and exchange throughout the body. With these nodes and these neurons, as far as we know, they relay information that is dynamic, including blood pressure, the oxygen level, pain signals, and inflammation. All these real-time information are relayed back to the heart, and then the brain makes a judgment call and the subsequent response. So as far as we know, this is roughly the human body mechanism. And I think there are some similarities to our water supply system. At TWC, when the total length of our pipes is over 100,000 kilometers, and that includes the micro pipes. And this is very similar to the neurons inside the human body. We have monitoring points of 33,000 monitoring points and growing. We also have over 4,000 networks, smaller networks. So these information scattered every day is passed back into our central control center. And then the big data is analyzed by the system, interpreted, and provides directives. So this is rather similar to the human system. Of course, the human body is self-regulated and it's autonomous. And what we hope is in the future with this continued SCADA, and we can incorporate all these applications and in the future to make it also autonomous. This is our company deploying various systems, and this is the history of how various systems were built. As early as 2008, we completed our GIS graph systems, and this is infrastructure. We have the basic pipework, the ancillary systems, the pools, and various stations. In 2008, we built the system. 2 years later, in 2010, we completed our operation management system. And that specifically refers to our users, user information, new installations, and locations of the water meters, their external pipe work. All these are built in 2010 into the total system. And another milestone was in 2012, we provided a monitoring platform for supply. All the SCADAs and all the small network websites and information are pooled in our control center, and that's a lot of data. Then in 2017 and 2018, we began to attempt in applications leveraging these systems. In 2017, we completed the inquiry system for water stoppage announcements. This was mainly manual, based on the locations of the smaller networks and the roads. We describe the water stoppage areas, and then the announcements are sent out to the affected users. In 2018, we finished a report back platform for user status. In this year, there was a big earthquake in eastern Taiwan, Hualien, and we built the system at that time. It is similar to the app Who's Call. It's a user feedback platform. When the user looks up their information, they also report back the real status. And then at our company, we can make judgment calls based on that. We have two other systems which are in progress. We hope that in the future we will continue to develop systems based on existing big data and AI technologies. This way, in the future, the system can automatically generate information that we need and automatically help with operations. These are some of our future plans. So with our automatic water stoppage announcement system, that we are currently improving it and upgrading it. In 2017, it was mainly manual, and now we're testing a new system. Basically, it's still built on the small sub-network idea. So with the smaller networks, we have SCADA, stats, historical data, current status to make these calls when it's 20% or 10% water pressure, then automatically we have some response. And then we can automatically generate a water stoppage areas rather than having to do it manually. Likewise, when these smaller networks, when the data are coming back to normal, then it can make judgment calls. So that means we have a dynamic system response. And this cuts the response time required for manual allocation of water stoppage areas. And
the other thing is relevant to the issue we are on the pending, because on the online we can conduct immediate hydraulic analysis on the line with regard to the change of the water supply regarding the reference for the hydrolysis analysis. This includes the established set, including the relevant system to be operating. Okay, so next I would like to briefly to go through this with regard to the overall what I said regarding the status of all systems. So this is, I think, for all units, basic information are more or less the same or similar, including there are some, including certain parameters, and then the attribution or position search. This just like that, because for all the relevant information are established for search or source. So then this is the operation management system, 1 in 500, the map. So basically, as I reported earlier, basically to not only on top of the user's basic information, and you can see the location of the meter, location of the user, the location of the switch, and then even exterior piping, all the information will be here. So therefore, so all the systems are just presented. So overall, it is all compiled under the same basic map to establish and accumulate all the information on the same layer. So it's for the convenience of the information share and sourcing. This is our back in 2012 regarding the water surveillance platform. Here, I would like to share with you earlier regarding the Mataian, the barrier dam. So the water supply at Mataian. To show you, this is during the disaster, the water outage, basically for all the supply, all the SCADA. Have no information at all. But certainly some of them are just signals. Some of them are the damage of the devices. Mostly are just because in reality there are no water pressures and the water flow to be measured. So you can see it reflects that some abnormality. I'm sorry. These are just some warning signals. So these are with regard to the water supply resume normal. So this is the same map regarding the surveillance. Basically, there are mostly all green lights. Everything is normal. Water supply is back, resume. Some of them are blue light, and perhaps the water pressure is a little bit higher. I would like to highlight this because in Hualien area, when we supply the water, because there are many the foreign particles, including the flushing at home, people need a large amount of water. So back then, we especially increased more water resources, including some like the Water Resource Agency, including Taiwan Sugar Company, including our the private wells. These are the area around the water influx, so the water pressure is a little bit higher, and there are some outage signals, and which we will recover immediately. You can see this is a very busy map because earlier we tried to identify in Guangfu County because relatively they have a less population. You can see this one in the urban area regarding the platform for water surveillance here in Taichung. You can see the old district. There are 8 districts, including Dali and Taiping. As you can see, within this the district, in this proximity, we have about 1,500 surveillance spots. Out of that 1,500 spots, we have divided into 126 segments. So relevant data is very huge every day. Basically, you can see mostly is present from the historical data under the normal situation, either so high peak or low peak. If it is normal, basically we will say to like a 2-fold or 3-fold deviation. So it is so-called the normal water supply. So here you can see 126 segments. Okay, so here I just happened to, trying to show you that. So here, this is the map. I want to show you this map. Well, this is from Penghu Smart Water Supply System. I just happened to show you this map. Basically, it's, because last year we have established this system. Why? Because we use a prospective project budget. So we have a budget to allocate to Penghu. Basically, in Ma Gong, we have divided into 6 different districts. So all the users, we have like 5,000 users with smart meters. So under the 6th district, we have embedded into the smart water network to conduct statistics, analysis, and inline, immediate response, including individual water usage, because we have more than 5,000 meters. So the budget is rather very huge. Okay, this is back in 2017. We have outage announcement because this is a menu set of either the green area or outage area, or the green area is purely a menu, either there's a mobile phone or tablet you can search, and it will bring out the user's location and make an immediate announcement regarding the water outage. So at the moment, the announcement, in early days, people leave their mail or line or phone. Now, if you log in, we will use a line. If there's an outage, short notice, we will have an immediate announcement regarding relevant water information. Okay, this is the EMIC. Once it is spontaneously established outage, we will use an EMIC system to conduct the outage information here. So this is users' water supply feedback. As I mentioned earlier, this is like a with code. So the user will feedback the current status to the company. So for the system to process, basically this is with the basic information, whether it is on the outage area. If not, then the message will be feedback to the company, and the system will display it. Because if this area have no outage, but how come so many users reflect that? So it means that there's a water supply abnormality, so we will take care of that. Okay, this is in the future. We hope that at the moment, right, under testing, so it is a pilot system. This is a rather dynamic system. Like I said earlier, it utilizes the concept of small network, and then you collect the historical peak data to make a justification to create this automatically. When it resumes normal, it will reduce automatically. It is a rather dynamic run and dynamic system. This is under testing. So this is under development with regard to the water analysis system for your reference. This is just a pilot system. Next, I would like to share with you two Taiwan water power company have applied it for years with very good achievements. So that is AI supportive technology. First of all, it's AI supported water leakage testing with the help of the industry. So this AI supported water leakage analysis. This is collaboration between Taiwan water company and ITRI. There are 3 stages. Nowadays, it's still under optimization. The primary concept is that we want to develop the identification module for the water leakage root cause, because the environmental change, the material of the pipe change, and then the reason of leakage will be different. So we hope to establish something that a database for the water leak. So in other words, we want to inherit the experience from the masters, the senior masters, utilize AI analysis or diagnosis about the pipe leakage. That's the basic concept. Under the first stage, the efficacy is very good. We can reach 80% accuracy. Second is to establish a fast screening, utilize non-professional staff to conduct regular screening, and then have the professional staffs to review, double check the AI data to save the labor and time. The third stage basically will expand the area, and then to continue to test or optimize the module. Okay, on the right-hand side, it is the flow map. Basically, on the blind test, fast screening. This is for your reference. Okay, basically. Okay. Okay, now, basically, as of this year, this July, we basically have done some analysis from AI diagnosed kilometers, which is about 3,000 kilometers. So the verification of leakage have reached 1,570. So we will continue to apply or implement this one. And after the analysis, we found out that it came out with AI-supported leakages checking either on the labor or on the time or the overall cost, actually. So the performance is very good. We save a lot of labor. Actually, labor saving is expanding, and also we reduce the time for the screening. We also save a lot of budget here. So with all respect, the performance is very significant. So the second I want to share with you regarding AI-supported technology is that our WADA system, Water Advanced Data Analysis System. Okay, so this system, basic principle is that it utilizes a overall long-term historical data, and long-term historical data, including the water pressure and the water flow rate in the small district. With that historical data, we can conduct certain the justification basis. So for this water system, it can conduct. It can link to our GIS system. It can interface with the water supply platform, and also under GIS system for the small district network. For all the statistical data or historical data, establish online the data to create a prediction. It also will use mathematical algorithm to predict whether this small district have some water supply abnormality in the future. That's the basic principle. Perhaps some of the algorithms have some modification. However, at the moment, so the theory is just like this. So this is our a self-developed system. So out of the 4,000 small districts at the moment, there are about 3,002. About three-quarters of the district already linked to this system to conduct a long-term analysis and analysis. If there's abnormality, it will report local site to conduct a further process. Okay, this is about our flow map, about basically from historical data through algorithms, all kinds of algorithms to generate the report and inform local site to conduct the site the check. This is just for prediction. All right, this concludes Taiwan Water Corporation's application on AI. Thank you very much for your listening. All right, thank you very much.
We heard from him how AI can be applied in water supply management, monitoring, and even pipework risk assessment. In the interest of time, we will keep the questions from the floor until the end. And now let's welcome Professor Chen Jun-san from NTU Civil Engineering Department to talk about AI 2.0. He co-founded the AI Center and National Technical Secretary General, Director Dong, and Mr. Wu, Professor Vojnovic. I try my best to pronounce it correctly. Excuse my pronunciation. Distinguished guests, ladies and gentlemen, good afternoon. It's a great pleasure to be able to share with you the things that we are doing. My name is Chen Junshan. I work at National Taiwan University, NTU. I am also the director of the NCREE NTU CEAI Center. We have a center here on AI because most of the time AI is used in other in non-engineering applications. So we set up an engineering-specific AI center. So I'm going to talk about the topic of AI 2.0, its definition, the opportunities it presents, and how we can transform it into something useful. So this is AI. See? Oh, that's AI. It's not very practical, but we can make it into something practical. This is our team. Basically, a group of students. A lot of examples here. These case studies are the collaborative work with Sinotech and eTree, as well as NSTC, and also many splendid engineering company. They actually send their staff to become my students. So you can chat with them about how an engineering consultant company can leverage AI in their work. Let's talk about 2.0. Starting with 1.0, we know that there's a lot of data. We label it, and then we can have a predictive model. So you have lots of data, and that's very useful. But the key here is labeling. That's the difficult part. We have lots of data, but very little that is labeled. These are rebars. We can scan them and then get the sizes. What's this used for? This is to confirm before the concrete is poured that it complies with the design. But this is kind of not useful now because we cannot get any workers to tie the rebars. So you cannot be too picky on them anymore. We are willing just to have hands on deck. AI 2.0, the reason we have it is because it takes too long to label all the data sets. And that's why AI was stagnant for a while, because we didn't have any labeled data sets. But AI 2.0 is something else. We look at LLM, large language models. And how do we look at 2.0? We just need some data. They don't necessarily have to be labeled. It's a different idea. I can talk about it in details. 2.0 is more like a person or human. So if I'm not here, I ask AI to talk, you probably won't be able to tell the difference. So next time, maybe I'll get an AI agent to come here and speak to you. You won't be able to tell the difference because AI has now passed the Turing test. If you don't see this robot, actually, you would think, and you just hear him or her, you will think that's a human. So how smart is the new AI 2.0? The latest GPT-5 Pro. This is a standard IQ test. Mensa Norway quiz. You can take this quiz. I'm sure you are smarter than this. Now its IQ is 143. And the average human is 100. That means one out of 333, you have one person that can match the AI. I'm sure there are many of you in the audience, but not me. So this is a very smart AI, and it's going to move toward 160 one day. And so this is called general intelligence. Not an engineer. It's just very smart. That's all. The reason I highlight that is because I asked it a water sector question. It goes as follows. If during its development, a site spans 2 or more drainage areas and the original drainage and catchment areas need to be modified, which regulations apply? I was going to do a Slido voting, but in the interest of time, I will just tell you. So I tell AI to pick one out of the four. You have 25% chance of getting it right. Which act applies? We know that first two don't seem right. We just need to pick. So this is what AI picked. Article 10 of Water Resource Act, WRA. It seems quite reasonable, and they tell you the proper answer is this. This is what's scary about AI. It gives you all these reasons because of this and that and the blah, blah, blah. So you believe that it is right, but actually it's wrong. So I will cover it up because it's all wrong information. So how do you turn it into the right answer? So how do we turn AI into general intelligence into an engineer and understand our language? This is RAG. This is my main theme today, retrieval augmented generation. Actually, you do it quite a bit. You give ChatGPT a PDF, and then it understands. And so you give it some external data source, and then it compiles it and gives you an output. So this is called RAG, retrieval augmented generation. This is a standard way of doing it, and you have to do this. Otherwise, it doesn't have the correct information and knowledge. The principle of RAG is quite simple. Basically, he uses the retrieve content to generate content. So it's grounded in real-world knowledge and context, just not pre-trained data. So it reduces the likelihood of hallucination. You give it external data sources. So now let's see if it works. And let's apply the same question. So this is the drainage control manual, and you can download it from online, and it has over 134 pages. For a senior engineer, they would know that only 50 pages are important. So you feed this 134 pages into RAG, and it tells you this Article 3 of Drainage Management Rule applies. And it took it less than 1 minute. This is the power of AI. You cannot read it so fast as a person. So it reads this information, it understands, and then gives you the right answer. And that is the right answer. So this is RAG. So how do we turn it from someone who doesn't know engineering to someone who does? There are a lot of techniques, RAG being one of them, and then prompts. It requires techniques as well. If you want to do it well, then you need to fine-tune your model so it has permanent information rather than having to feed it every time. So two things to this. First is there should be sufficient external knowledge. Second is you need a fine-tuning. So these are the two techniques that we can transform. And the other thing is also very easy to use, the agent. As Mr. Wu said, that's exactly what an agent can do, the core of AI. You can give a lot of tools such as GIS with a lot of data that's searchable. But these things you don't need to get AI to do. You should get tools to do this. For example, 1 + 1 is 2. Don't ask AI to do it. Ask a calculator to do that. So with these answers, you can get tools to do it. An agent is very popular now. You see examples on the internet a lot. You can go do searching on the internet, make a travel agenda, and book an air ticket for you, and then you're ready to go on your trip. So an agent can go online, conduct a search, and through memory and actions, they can give you a plan. Looking carefully now, it's no longer about answering a question. It's about completing a task. It's more and more like engineering, which is where we complete a task or several tasks, and it involves several aspects. So that is what an agent does. So these are a few things that are sufficient to turn very robust AI into a robust engineer-like agent. So here are some case studies. The first one is a more difficult one. We looked at a document, a PDF of text. Text is easy. Well, we shouldn't say that it's easy. It's okay. We can just screen it, and there shouldn't be too many problems. We want to challenge a more difficult problem, which is images or drawings. We know a lot of engineering knowledge is buried inside drawings. So can we find the information we're looking for from drawings? That's a key. This is a contract administration, a construction administration example, supervision of a project. Maybe has less to do with water sector, more to do with the construction sector. So this is the Danjiang Bridge in New Taipei. And in a typical construction project, you have the design, construction, and supervision stages. In construction supervision, there is a very painstaking task, which is you need to follow the specification, the design drawings, and some design models to generate a form. This form is very difficult because it depends on where the project is located and some of the details. With the Danjiang Bridge, we need to worry about chlorine ions, which doesn't apply to any other site. So an experienced engineer can generate a good form like this. And once you have that, it's easy to make it, to electrify it. So you can use your phone and upload it online. This is not the hard part of digitalization. But the hard thing is to turn from all these unstructured information into a structured information. In the past, we didn't want to do it because it's too difficult, too many rows. This is extremely time-consuming and experience-dependent. So the most challenging part is the drawings. So what I want to do is to do drawing traceability. An engineer writes this, and I want to verify if it's correct or not. So someone drafts it, and then usually less experienced, a more junior engineer drafts the form, and a senior engineer comes and review it. And so now let's try and use AI to do the checking. Out of the over 1,000 drawings for the bridge, the engineer must, out of all these drawings, find the right drawing, and out of the drawing, find the right sub-drawing, and then the right information, insert it into the form, and then put it into the checklist. So basically, this is chunking. You have a lot of information, and you need to chunk it into and cut it into little things, and then find the right information. So if you don't do anything and just ask AI to do it, at best you can get 20%. With not such good AI, you have what's called 4.0. 3%. 20% is actually 20% correct ratio is pretty good, but what we have done is exactly the same as what we did before. We learned how an engineer does it, following the same reasoning logic and the same retrieval logic. So the retrieval and the reasoning need to be domain specific. And then we can have almost over 80% accuracy. It's pretty good already with a simple drawing. If it's not 1,000, let's say just 200, 300 drawings, we can get 100%. But this is a really complex case, so it's slightly lower. Some details here that was skipped over. So different AIs, not all AIs are equal. 4.0, 3%, 04 mini, 20%. 05 is not open yet, so I haven't tested. With the addition of some domain knowledge, you can reach something like 80%. So that's where the difference comes in. it's quite easy to use this. You just input it, and you have the template generated. You fill in the blanks, and then how long did that take? 5 seconds. Where is the drawing? Which one? And then you can cross-check it. So this is a standard way of doing it. So at the center, they are applying this to practice already. Of course, in the end, you need an engineer to make the call. So it saves you time. We find that it's tenfold time saving, speeds up the process by tenfold. So what AI can do for you is one engineer can have 10x, can have tenfold performance. This is even a better case study. This actually tells us that knowledge, if you can clean it up first, then you can better enable AI. How do you clean up knowledge? It's called knowledge graph or ontology. Cleaning up knowledge is about 30 years ago, we did some knowledge management, and it didn't work out very well. And that is because it's too tedious. It's hard to manage knowledge per se. But now with AI, we can leverage a lot of its power. So then now let's see how we can clean up knowledge and do more. This is an example. These are knowledges. So for example, now I'm writing a safety assessment for a dam, and there are some chapters, and we need to review the flood analysis. We can see the rainfall documents, the frequency analysis, probability. So you need to link them and see what the relationships are. Optimally, we should have these relationships already called out. Then it would be easier for AI to use it. So that's what we call the knowledge graph. So these ChatGPT and LLM together with knowledge graph, we can do a lot using this combination. So bringing together LLM and KG, we can retrieve info, generate info, etc., and we can do it very well. In the past, when knowledge is generated or knowledge graph was generated, was time-consuming and manual. But now LLM can help automate and accelerate knowledge graph creation, so you can spend your time checking to see if it's correct. So for a business in the future, it's about knowledge graph and knowledge management. It could be structured, non-structured, email, experience from a skilled labor. This is the greatest asset for a company, and you can do a lot once you have that. Leveraging knowledge graph and agentic AI or agent, you can do a lot of things. There are different patterns, 6 common patterns for agent, and then you can do a lot with this combo. 2 examples here. First is how to generate a dam safety assessment. Second is compliance checking. The latter is very important to a construction project. So this is a dam safety review. It takes a lot of time to write a report. No one wants to do it. So based on the latest information, how can you update a report? That requires expertise. This is what we do. First, we establish the relationships between knowledges. So that's what AI can do. Past reports can be built. The knowledge graph can be established. Of course, you need to do some checks. And then after that, you can feed that into AI with the knowledge graph and updated info. So you have the knowledge graph, which is the existing links between knowledge networks, and then you feed in updated data. Then you can generate an outline and write a report, how to refine and check the report, and finally a reviewer coming in to see if it's well written. So, uh, so there are a lot of things that AI can leverage. The biggest responsibility of an engineer is to do all this correctly, and then the rest AI can help. So it's about planning the relationships, the information, the chapters, the sections, the related graphs. So you feed information into it, the system reads it, and the AI starts drafting it. And they ask you, oh, if it is, whether this is the good plan, and then generates a plan. So this is a report generator. After you've drafted a report, there's a review process. This is to check the professional quality, but the other aspect is the compliance checking. So we could check the report for compliance in identical process. So first, we find all the specs, rules, regulations, and then check each one of them to see if there's compliance. So AI generates a checklist first, and then see the results of the checks. So this is a knowledge graph. Likewise, I have a little program here. You upload the specs and the rules and regulations and your checklist, and then you feed in your report. Then it uploads, checks, and you see compliance, yes, no. And then if it's not compliant, then you just make some revisions. So this is quite useful. So using knowledge graph and agentic system, we can do a lot of things. Once we have cleaned up the knowledge and structure it, you can save a lot of time. You can write all these reports just as examples. There may be some reports that you are more interested than others. Quickly, let me summarize. First, what I want to say that AI is no longer a predictive tool. AI is talking and thinking like human, just like me. So how do we train it to really help us? That's the first message I want you to take home. Second is integrating RAG, fine-tuning agentic workflows, and knowledge graph to build an intelligent system that understands, reasons, and acts in engineering. I think there's going to be more and more application to check for consistency front and end. So I think in the future, it can check for consistency across drawings, text, images, etc. If you are interested in learning more about AI, I welcome you to attend my class. Just send me an email. And for those of you who are younger, I encourage you to come to our graduate school. I'm sure you will perform really well because you can bring your real-world problems along with you and actually solve them in our classes. If you want to go fast, go alone. If you want to go far, go together. That's what engineers do. We go together and go far. Thank you.
好，非常感谢陈教授。
Thank you very much for Professor Chen's excellent presentation. Actually, from Professor's presentation, it kind of opened my eyes, including all the reports can be generated by the AI, as we know that. So this will really help us to solve the labor shortage issues. But for the hydraulic work will be replaced by AI. That's joking, so don't worry about that. So we'll take a break. Next is a 30 minutes break. Invite you to enjoy the refreshment on the lobby. After the break, we will conduct the second half of the meeting and the panel discussion.
Minutes tea break. After break, we will have our afternoon section of exciting speech and panel section. So please enjoy the refreshment outside. Thank you so much. 各位现场所有的贵宾们，大家午安。下半场会议即将正式开始，我们邀请到下半场的主持人为我们进行引言。有请国立成功大学水利及海洋工程学系董东锦系主任，欢迎。Welcome back. The next session is starting now. Please welcome the moderator of this session, Professor Dong Dongjin, Chair, Professor and Department Chair of Hydraulic and Ocean Engineer, National Cheng Kung University.
Thank you. 好，谢谢。
Okay, thank you. General Secretary Jen and the other moderators, speakers, ladies and gentlemen, and friends online, good afternoon. I am Dr. Dong Dongjin from Taiwan. I'm very honored to serve as the moderator for this Water Week. And I'm very honored to serve as one of the moderators today. From the two speakers' excellent presentation after that, next section, we also have two speakers, including the experts from Netherlands, Professor Zoran Vojinovic from Netherlands, as well as the Dr. Zhou. The first speaker, I would like to invite the expert from Netherlands. Allow me to use English to introduce
Excellent presentation earlier. We are pleased to welcome our third speaker, Professor Roland Vojinovic from IHE Delft in the Netherlands. So Professor Vojinovic has over 25 years of international experience in fraud modeling, risk analysis, climate adaptation, and hydrological information systems. He has served as a consultant for various national governmental and cooperate with organizations such as European Commissions, Asia Development Bank, World Bank, and the United Nations Development Programs. So Professor Roland also led several large-scale European Commission P7 and Horizon 2020 projects, coordinating research teams across Europe and to develop the European Union's framework for nature-based solutions. So Professor Roland is also the international advisor of Water Resource Agency and also the adjunct professor of National Cheng Kung University. So today, Professor Roland will speak on the topic green and smart unlocking climate resilience through nature-based solutions and digital technologies. So please give very warm welcome to Professor Roland Vojinovic. Thank you.
Okay, it's all working well. Thank you very much, Professor Dongjin. Also, good afternoon, everyone, and it's my great pleasure to be part of this event and to present some of the work that we've been doing as part of the EU-funded projects. So the title of my presentation today is about the green and smart and how do we unlock climate resilience through nature-based solutions and digital technology. So first, I will talk about the nature-based solutions a little bit. Then I'm going to talk about the digital technology, and then I'm going to talk about how to combine the two into the notion of climate resilience. How do we achieve climate resilience? Just a couple of words about my personal journey through hydroinformatics. My background is in hydrology and hydraulics, and I worked pretty much all my life, all my career in the area of nature-based solutions, modeling, designing, and implementing such systems. But speaking about the AI, which is the focus of this event here, which is really in the application of water, is the hydroinformatics. I really started off with my MSc degree in 1998 in fuzzy logic models and decision support systems. And then I followed with my PhD in hybrid modeling, where I used the hydrodynamic models, physics-based models, with the AI technologies. Back then, there was the, we've used the artificial neural networks and support vector machines. And then I got involved in many projects, mainly European Commission-funded projects, like Switch project in FP6, and later on there were other projects. The latest one that we are working on and closing now is the Reconnect project, and there is another project called Artifact, dealing with artificial intelligence for flood management. So basically following my work on the hydrology and hydraulics, but also very much in the connection with AI, I've managed to produce more than 200 publications. I had more than 20 PhD students, more than 100 MSc students, and in terms of the research grants, I managed to obtain more than 30 million euros. And really, all of these topics are there. And of course, throughout the time, I followed from the artificial neural networks and fuzzy logic models and support vector machines through the use of the evolutionary algorithms and genetic algorithms, particularly. Also, I worked with the cellular automata, which falls into the area which is a computational intelligence and closely related to AI. I worked also a lot with the agent-based models for emergencies and policy development. And really, later on, we had some applications to the COVID-19 problematics. So with my students, I managed to obtain some, to get some awards. The student on the left from Thailand, she worked very much on the area of nature-based solutions and application of artificial intelligence, and particularly genetic algorithms and other technologies. And on the right is my student who got the not only cum laude, best cum laude, but also he got gold medal for his work on the use of the agent-based models for flood management. So going back to the topic, and I think it was very well introduced today by previous speakers, particularly in the morning. Carla mentioned a lot of things. He talked about the pressure that urban water managers facing nowadays. So it's not only climate related, but also it's very much about the urbanization systems which are aging, and there are other pressures. So altogether, it's bringing a lot of challenges for water management. We have in one year too much water, in another year, or in the same year, we have too little water. These are some examples from Europe in 2021. This is in July, in summer. You can see a large scale flooding that took place in Liège, in Belgium. But then the same event also took a lot of damages, and even 243 lives were lost in Germany, same event. The same event also affected Netherlands, but in the Netherlands the impacts were much smaller, and there are reasons for that. One of the reasons is that there is a large-scale nature-based solutions project implemented, and on top of that there is also a very good early warning system. So this is the Dutch experience, and then what you can see here is that during kind of same time in the Netherlands, some areas were flooded, but they were very, very flooded and controlled. They were controlled, so the flooding was controlled, and it was very much confined to certain areas. What's also interesting in the Netherlands to observe is that when such events happen, people are not scared from those events. They even go and do all kinds of recreational activities. So the nature-based solutions really are providing a large level of, high degree of safety to many areas around the Netherlands. So speaking about the other side of the coin, the droughts, so the summer 22, it's one of the kind of on the record, one of the biggest years in terms of the droughts that took place. This is along the River Rhine, where you can see some areas were really depleted. And then this is again, I took some recordings. Typically here the water level is much higher, but then, and all of these has been used for the navigation and the shipping. And then, of course, during the low water levels in Rhine, then the other means of transportation needed to be used. So, and this is another river, so the river that comes, so the main river that comes to the Netherlands comes all the way from Switzerland, the Rhine, and then the other river is the Meuse that comes from Belgium. Also records in terms of the floods, but also records in terms of the droughts. So some of the aerial images, what you can see here is the 2021 and 2022. 22 is a particularly drought year. And really, out of last 5 years, the 4 years have been declared as drought years in many parts of Europe. So, more examples of the aerial images that you can see. So now the question is, how do we respond to that? How do we respond when you have too much water and we have too little water? Obviously, we need to build a climate resilience. And there are different definitions of resilience. This is one of the definition adopted by the IPCC, which talks about the climate resilience being the capacity of different parts of our systems, economic, social, environmental, and so on. So it's the resilience is actually the ability of the system to respond and to cope with different pressures. There are other definitions. The next one can be the UN-based, for example, definition, which is the climate resilience refers to the ability of systems and communities to anticipate, absorb, and to accommodate or recover from the effects. And the last one I'd like to show is the EU definition, which I like pretty much the most of all of them, which states that the climate resilience is the ability to anticipate, prepare for, and respond to hazards, events, trends, or disturbances related to climate. So it is all about the basically developing the 4 key capacities if you want to be resilient to climate extremes. So you have the anticipatory capacity, which is the ability to foresee, to assess, and to prepare. Then you have absorptive capacity to withstand and absorb the impact. And then you have adaptive capacity, which is to adjust and learn, and transformative capacity, which is systemic and structural changes. So these are the key elements. If you go to disaster risk science, you will find that these are the key elements that define the process of gaining resilience. I'm sorry, my throat is a little bit suffering. So if we want to build the resilience, we need to work alongside of all these capacities. And to respond to this, we typically go with traditional measures, which are engineering structures, which are gray, the so-called gray structures. But then nowadays we are moving increasingly towards the green infrastructure or the nature-based solutions. That's a typical example. This is the example in Singapore, the Bishan Park. On the left side is 2008, how the park looked like and how this channel looked like back then and how it looks now when it is completely transformed. So besides the typical nature-based or gray infrastructure, we also have a social and governance solutions that form the part of the solutions towards climate resilience. So if we compare the different characteristics between the gray and the green infrastructure, this is not to undermine or to neglect the importance of gray infrastructure. So gray infrastructure is very much important. This is not to favor one over the other. It is to say that really we need to look into more hybrid solutions. So the answer is not in left or right, it's really in the combination of the two. But then you will see later, it's also in the combination with the digital technologies. And what we've heard here today, there are many areas where we can enhance the functioning of our infrastructure with the use of digital technologies. So these are some of the kind of comparative sites that the gray infrastructure is very much engineered, structured. The other one is using the natural processes, and so on and so on. You can find so many different kind of features or characteristics, and that can be easily found from the literature. So when we talk about nature-based solutions, and this is one of the examples of the European funded project called Reconnect, this is the area in Denmark. It's called Aarhus. And what you see here is that we have coastal area, we have urban area, and we have large detention storage area here, which is in actual fact, the nature-based solution for this region. So when it rains, the urban area here gets protected by the water being stored in this region, and that's retention basin, if you wish. And what is interesting about it is the way how it's designed. So it provides multiple benefits, not only in terms of flood protection, but also provides multiple benefits in terms of biodiversity and species. And then also it provides multiple benefits in terms of the recreational use by the local residents. So, so what happens when this area gets flooded? Typical grey infrastructure will not have much potential for, in case if you have some cascading effects, if one hazard cascades to another. With nature-based solutions, we have seen that, and we have demonstrated and we documented that they are very good also in terms of the so-called cascading or compounding risks, when you have multiple risks coinciding, but also when one risk staggers and goes into another risk. So you have a flood wave which potentially occupies a certain area, maybe creates a damage to the power fittings and things like that, but then you may have a shortage in the electricity, and you may have some other. So this cascading can be much easier prevented with nature-based solutions because there is a flexibility and room to do that, and we have addressed that in one of our projects that I mentioned before. So I'm not going to go much more about the NBS, but I'd like to just sum up what is the next phase of NBS innovation. Well, we need to advance more on the knowledge of processes, which is very much technological aspects. Also, we need to work more on the scale of implementation and the replicability of these measures. And then we also need to work more or learn more how to enhance the multifunctionality and multiple benefits from these measures. Also, what is interesting to pay attention on is the effectiveness from single and integrated solutions. Carla mentioned this morning that these solutions can function very well in isolation and we can follow them, but then how they work in connection with other types of infrastructure, not only green, but if you have a whole chain of these measures, that's a particularly interesting question because that requires systemic analysis or holistic analysis. What we also need to pay attention on is how to better integrate them with the ecosystems, holistic assessment, and the final thing is how to enhance their effectiveness or benefits with the use of digital technologies. And this is where I'm going to head into now. And this is where the AI can play a very important role on how to enhance the benefits of such measures. So why digital science and data? Well, we all know that the quantity of information is increasing nowadays with the high rate, great speed. And I found a record that in the last 3 years, 90% of all data in the world has been collected in the last 3 years, pretty much. And we have developed the abilities to measure, sense, and monitor almost everything. Carla again mentioned today about some sensors, and we heard also from other speakers. So we can pretty much sense and collect the data about anything and everything nowadays, and we are very much connected with our devices. So then what is particularly interesting for us when it comes to flood management and nature-based solutions, we will need to tap into the area, and we are tapping into the area of AI, and here you can find all kinds of different technologies that relate to the field of artificial intelligence. Artificial neural networks, convolutional neural networks, recurrent neural networks. These are very interesting. PINs, physics-informed neural networks. Because neural networks are very much labeled as black box models, learn on the basis of input-output data. But here in the PINs example of neural networks, we can incorporate some governing physical laws, such as Saint-Fanon equations or Navier-Stokes equations, and then use the neural networks to enhance this performance and to fasten the computations. Graph neural networks, support vector machines, and so on and so on. So there are many different technologies. And as part of the hydroinformatics field, we've been looking into all of that. So talking about I mentioned before about the project called Reconnect. And here, as part of this project, we have managed to tap into some of these areas to look into how these areas can help nature-based solutions or enhance the performance. And I will show you some examples of that. So that's a project which combines more than 35 partners, 6 years. We are in the process of closing it. And we had a number of locations where we looked into these systems, and one of them is also here in Taiwan. So the digital solutions that we've positioned in this project is very much done in this fashion. So where you have stakeholders which have ability to draw on all kinds of data that are coming in real time, but also from the area of the digital technologies such as the early warning system, impact-based early warning systems, and then the whole field of AI. And then the stakeholders would draw all this data to develop scenarios for different climate options and try to look into the functioning of these measures. I'm not going to go into the details of the project. You can find the website, reconnect.eu, and you can find, we have more than 70 publications, and we have more than 70 deliverables. And we have published also some nice books as part of the European Commission on topic of nature-based solutions. So in this project, we've worked together with many other projects, and I mentioned also that there is a particularly new project that's running right now, Artifact, Artificial Intelligence for Flood-Resilient Infrastructure, and you may visit the website. In the Reconnect project, we've been monitoring nature-based solutions in real time. We also use the underwater drones to go and to look into the areas of where these systems are. So in this project, we have only collected the data, but now we are going next step ahead. So with this data, we want to use the hyperspectral camera images. So instead of going into old-fashioned way, collect the samples and go to the lab and analyze, now with collecting the samples, taking it to the lab, and then training an artificial neural network model, we can, on the site, come up quickly with the water quality characteristics. So that's one area of application. And here we have been looking into some kind of neural networks or support vector machine to be trained with different images in order to come up quickly, rapidly with some water quality results. Another example that we also looked at was the area outside of Barcelona in Spain. So that area has nature-based solutions. They've used some examples from the Room for the River project, but they also have digital solutions, and they looked into some social and governance. So what was done here, in this case, is, I'll just quickly show you. So this is the area. We've had first we started off with the rainfall, and we had flow. We've used the support vector machine in this fashion with an input layer, output layer, and hidden layer. And then, of course, we trained the model, and we compared the results, because in Spain they're using hydrodynamic models and hydrological models to compute for different stations, rainfall stations, to predict the water levels in the rivers. So the SVM model runs much faster and produces equally good, if not better, result than the hydrological model and hydrodynamic model. And our next step is, and we produced some nice dashboards here to view that. So the next step is to go into the impact-based predictions. So now this time, what we want to do, we want to go between the rainfall and flow observations, and then provide the learning between the input and output being the results from the hydrodynamic model, and then relate that to the impacts. So then the next predictions will be in the sense of when you have water levels, we predict that. Then we go into particular damages and try to assess what kind of areas are most likely to be damaged and what kind of measures can we apply in real time to act upon it. Then another area of application that we've done where we looked into the AI for nature-based solutions was to develop a digital twin. So we've developed a digital twin for the Pathum Thani area in Thailand. So the digital twin concept is you take the data from the physical world into the digital twin, which basically embodies all these characteristics from the physical world to help you to make some decisions, which can be either operational in real time, like early warning, or it can be used for forward planning applications. So this is the Pathum Thani area in Thailand. So it's the area which is very much interconnected with a number of different canals. So there is a Chao Phraya River, there is a Passak and Lopburi River. And then what they have here, this is This is the Rangsit community, so you have a large number of different canals, and they have a number of pumping stations they use around. So the idea is it's a very much polder system. So you pump water from one part to another in order to increase the effectiveness. And this area has been quite successful during the 2011 floods. You can see the pink area depicts the flooded areas. This is the area that's not been really flooded. And then we are now enhancing that with the use of real-time sensors. And what you see here, we tried the real-time control application. That what you see in here is the without the real-time control, and this is with the real-time control, how much storage volume can be accommodated if you use the real-time sensors. You turn into your models and also some AI algorithms and try to operationally decide to divert water from one part to another in real time, and then you can achieve this kind of effectiveness. So that's another area of application. And that we managed to publish that in one of the Journal of Environmental Management. So finally, I've spoken about the nature-based solutions. I talked about the digital technologies and AI, but now the question is going back to the how to gain the resilience, or how do we, because we are doing a lot of developments in the measures themselves, like nature-based solutions, gray infrastructure, but then we are doing developments with AI and other digital technologies, but then how do we know that we are really gaining the resilience, or we are just developing something for the sake of developing? Well, a framework that we can do in this sense is that I'll quickly show you. Got a little bit stuck, I'm afraid. Maybe you can push it. Yes, okay, so it's really to turn all the work that we are doing, we try to put into different technology levels. So here is the example that we are following. It's not the answer to all the questions, but we try to reflect the NBS through the technology readiness level, digital and AI solutions through the digital twin level, then the ability for the society to adopt these measures. We turn that through the SRLs, societal readiness. Impact and sustainability level is another dimension which is very important, adaptive capacity level, and also replicability. So if you turn all of that, and I'm not going to go into the definition, there are frameworks on how to look into the different digital twin levels and what this means. Then basically, and societal readiness levels, then the thing is that you can basically combining these different levels, and we have publications for that, I'm happy to share it. We combine it into the climate resilience index. So you have these different levels addressing technologies, nature-based, and also AI and other digital technologies, and the societal readiness level into this kind of framework that we can combine into a resilience index. So then, by tracking what we are doing with our developments and how we are applying, then we know that we are raising the resilience rather than just doing something for the sake of doing. So that's one of the frameworks that could be potentially applied, and this is where we spent quite some time. The very last thing is that this artificial intelligence for flood resilience infrastructure is a project between the 4 institutions. From the, we have the Technical University of Delft, we have IHE Delft, myself, we have a Technical University of Hamburg as well, and then we have Institute for Artificial Intelligence that we are working together on this type of topics. And the very, very last slide is the 3 take-home messages from this presentation. The first one is that NBS have obviously becoming important means to achieve sustainability, flood protection, and the climate resilience. On the other side, digitalization, data science, and AI are becoming important means. And then the third thing is that the future challenges are not only technological. What I'm trying to say here is that we still need to work much more on how to integrate, better integrate with stakeholders, with communities, and not to get overpowered or by the technologies, but rather to keep the human component very much there. And that's why the societal readiness level and all the other dimensions are very important, so that we don't only get driven by developing technologies, but to leaving some social and other aspects on the side. And the last point is we are more and more increasingly getting required to work not only, we worked a long time in single disciplines like hydraulics or hydrology. Then we moved to multidisciplines, but then we moved on to interdisciplinary way of working. But nowadays we are working in a transdisciplinary. So what that means that we need to connect more with people from humanities and social sciences. And to do that, we have to really think how the AI can help with that. At the moment, we are lacking behind in that area, but this is going to become a challenge in the time to come. So thank you very much for your attention, and I'll be happy to address some of the questions later.
So thank you, Lauren. Very good talk. And we will have a question and discussion in the later sections. 谢谢Lauren教授。
Thank you so much, Professor Lauren. Now, we're going to proceed to our fourth and last speaker in this session, Dr. Zhou. Dr. Zhou is currently the CTO of GST Envirotech. He obtained his doctoral degree from the National Central University and is a qualified and registered environmental engineer. And he specializes in the practice and theory in water sector and has engaged in the planning design of several wastewater treatment plants and helped establish the sewage management system in industrial parks. In recent years, the team he leads has established the Water Ops Smart Water Service Platform, combining AIoT, edge computing, and digital twin technology to realize precision control and carbon reduction. The topic we will hear from him today is AI empowerment for smart water governance, from data to resilience management. Please join me in welcoming him. Dr. Zhou, please. Hello, everyone. First, I would like to thank the moderator for the introduction and the invitation from the organizers. I want to thank the WRA for advising me in preparing this PPT. We just heard from Professor Rowan and the algorithms. That reminds me that it's been 30 years since I came into this sector. Starting in 1999, the water management system went from information to automation. In 2005, the first AI application on water management, the first such paper. And then since then, I have been engaged in research in how to make the water management smarter. And now this marks the 10th year of this research work. So today I will share with you the work over the last few years, how we managed to connect all the technologies and how to apply them in practice. In terms of water resource management, when we look at the missions and challenges, we can look at it in the following aspects. First is drought prevention and water status forecasting. 2, flood prevention and real-time control. 3, water resource allocation, supply-demand management. 4, wastewater treatment and reclaimed water promotion. And 5, admin management and decision support. So when we manage the water resources, these are the key missions. However, over the last few years, as we face extreme climate, the alternating floods and droughts, and we heard in 2021 the water shortage and all the frequent floods that we have seen in the last few years. Also, individual water management agencies, they have extensive monitoring data, but the question is how to integrate them. And next question is how to use AI to enable decision based on this data, and how to use the data to manage our systems in real time. Finally, the general public and their expectations on the administration and governance of water resources, and the expectation for transparency and more stable water supply. With all those in mind, in the last few years, what we have done is to connect all the AI technologies. We call it the AI empowerment technology chain. First, that includes the following: data sensing and communication layer, data management platform layer, data analytics and modeling layer, decision support layer, and finally, real-time feedback and control. So we have developed these 5 layers. To the right, I won't go into too much details in the interest of time. To the left are the technologies leveraged, and to the right are what's being done with each individual layer, the tasks, and how to achieve the goals. So I've compiled the information here. Basically, for the sensing and communication layer, using our IT management system, first of all, we need to enhance the real-time and accuracy of hydrological monitoring and provide reliable data foundation for droughts and flood prediction. At the same time, reduce the frequency of on-site surveys by the workforce and enhance the immediacy of disaster prevention. And for the data management platform, we use it to improve data consistency across agencies and enhance policy transparency. On the data analysis and modeling layer, first, the goals we want to achieve is increase accuracy of drought and flood early warnings and to increase the response time. And next, to enable science-based decision-making, reduce human judgment errors. Decision support layer. Our goals there are to accelerate decision-making processes and shorten reporting cycles, and improve transparency and strengthen citizen engagement. Control and feedback layer enables us to shift from reactive response to proactive prevention and reduce workforce dependency and operational risks. So in applying the AI technologies, we need to set forth clear goals and targets. So overall, with AI empowerment, we go from the collection of data, predictive modeling, to decision support and automatic control, to establish a smart management mechanism. And this way, we can move from passive response to proactive, intelligent, and sustainable water governance. And here are the key benefits: resilience against disasters, sustainability, transparency in governance, and efficiency in operation. When we were formulating the AI empowerment technology, these were our strategic goals, and I've compiled them here for your information. In developing applications for AI-empowered technology, it has been a very challenging and difficult journey. So we look for representative projects and pilots to start off, and then slowly we scale up to applications. So now I would like to introduce our work for each task. First, this is something we're very proud of. In 2021, when there was water shortage, and we were able to leverage the WRA databases, rainfall prediction, and meteorological data from the Central Bureau. We also need to know how much water we can reclaim or recycle. Those were information coming from the MOE, but mainly data sets from the WRA. At that time, we developed this system called the Drought Early Warning Crystal Ball, with the following intention. If we, from historical data, we can see or build a model of the water storage in the dams, then we can simulate the situations. Under what scenarios will we have water shortage, and under what scenarios will we have sufficient supply, and should there be a drought? When we would reach the red light, green light, or yellow light. So we can enable the public and even high-tech companies to make early decisions. Later on, I will give you an example of a high-tech company using this information, so they can decide what kind of water strategies to take in as an early response. So in other words, we can use these models and predictions to enable business to know our future supply status, and the government can also act early to reduce impact from water shortage. We decided to pursue this model, and actually we won awards for this model. And the reason was we wanted to help prevent droughts and to adapt to water shortage. So using AI, we can predict water shortage risk days or even weeks in advance and enhance drought preparedness. And also, we can support reservoir allocation decisions, reducing the impact of water restrictions on citizens and industries. So the effect on drought prevention water situation forecasting task is we can improve resilience and support scientific allocation. This is a case study from a wastewater treatment pumping station. Here, we can think about how to use existing facilities and existing water flow buffers to control and prevent flood. For example, in this area, during the day and night, there is great fluctuation daytime versus nighttime. When there is rainfall, a lot of time there are very big storms. So how do we use these existing pumping stations to even out the water intake and to prevent impact on the wastewater treatment plants? That is the question we were looking into. So you can use this storage capacity and all these sewage systems. They can contain water, and you can save a lot of cost on utility, on electricity, and also to enhance the water treatment capacity by 3,000 CND. And also this can prevent frequent initiation of the pumps. And by doing so, increase the lifespan of the pumps. So in this case study, we see that we can use the application water level control at sewage pumping stations to improve the accuracy of storm peak flood forecasts, automatically recommend operations, and reduce the risks of human errors. So the effect on flood prevention and real-time control tasks is to shorten reaction time and reduce human errors. In 2021, during the water shortage, there some high-tech companies and factories were affected. So here we use a dynamic water supply and demand model to provide to inform a high-tech factory. So water supply is critical to a manufacturing plant. So here we have some dynamic simulation. As we heard a lot from today's speakers already, and Professor Chen mentioned this already. First, you need to establish the relationships. So AI has a path to follow. Without this kind of relationship building, the AI doesn't know where to go properly and even make wrong decisions. So we can use, this is also another digital twin system using digital simulation and model building under different water use scenarios. The recycle ratio, how do we boost the recycling ratio, and what responses can we make? So when there is water shortage, how do you secure different water sources? And we found that from the wastewater treatment center, they can reclaim roughly 20% of water, and this would resolve water shortage. So using this digital simulation automated decision support system, first we can do water demand forecasting and allocation optimization. So on water resource allocation, supply demand management, we can balance fairness, efficiency, and sustainability. Wastewater treatment plant. As we face net zero goals, the treatment plant in terms of carbon and energy reduction. Well, first, we can save energy on the processes, and we can use AIoT process control to optimize the operation. This is for the process part. So we deploy AI models to achieve efficiency in water treatment and benefits in carbon and energy reduction. And we optimize this. The second thing is for a treatment center, usually the first thing is about precise aeration control. And to achieve this, what we do is to feedback and fine-tune the controls. And we find that we can achieve at least 14.5% of energy saving using this. To cut energy use and carbon, there's something we need to pay attention to, which is chemical dosing control. Because with the chemicals, there's related carbon emission. So we can have precise chemical dosing control. In all our cases, we're able to have NaOH dosing efficiency and CI2 benefit improved. And at the same time, we also cut our sludge output. Equipment health management. This is with the flood control pumps under the management of WRA. We need to constantly monitor the flood control pumps. And when we need to use them, we need to make sure they are working, and rather than finding out when they need to be activated that they're broken already. So we need to have health monitoring and maintenance and repair management. So in terms of precision control and equipment health management, we can optimize wastewater plant operation, reclaim water monitoring, and smart inspection, and finally to improve wastewater treatment and have better efficiency. This is an example for administrative management decision support, our Water Ops Water SaaS platform. So we have a way to extract the features and clean up the data, and we have standardized operational protocols for all these, so we can have more efficient data cleaning. And recently, we are starting to look for faults or gaps in the data sets using AI. Also, when we are unable to secure the data, for example, most information are scattered, and now we have developed a system where we can extract from the SCADA screens and bring them into our platform. So when you don't have real-time monitoring data, you can use this monitor to extract info. So this is an example. Today we saw Mr. Wu also has a similar application. This is from the Taiwan Water Company, TWC. So applying our platform onto the TWC official website. So putting our platform on TWC's smart water platform and using AI to enable it. So this was a project on that. Digital twin and analog control technology. This is very well developed now. We have what's called a digital twin system. I apologize that I had animation originally here, but to make it smaller, now it's just an image. So in other words, we have a simulating system, and it simulates water quantity, quality, or certain changes in environmental parameters and how we can respond to that. So this is a digital twin system. Using the Water Ops platform and digital twin technology, we can automate decision support systems, and we can combine what we heard from Mr. Zoran and also from Professor Chen, how to combine nature-based solutions and large language models to provide smart customer service and knowledge management. So with all this experience, how do we integrate it into the platform? When there are anomalies, I can quickly, based on other people's experience, to decide how to operate, to control, and to be energy efficient. This way, we can improve policy transparency and public interaction efficiency in terms of administrative management decision support. Finally, the policy implications and future outlook. First, in terms of policies, these water resource management, they can support SDG 6 and 13 and also comply with ESG and net zero goals. And this morning you heard about the A+ project. So now we need to combine it to carbon inventory initiative, and that's our next step. Next, we can achieve efficiency, resilience, and sustainability on water governance. Future directions. 1, AI can become a new infrastructure for water governance. 2, international collaboration for sharing AI models and standards. And finally, data governance and AI ethics to ensure trust. In my next book coming out in December, this is AI technical guidelines. We'll talk about how we achieve all these in details. So this is a goal for myself, and I hope that we can all work together to illuminate the future of water resources with AI and create a new era of smart water services. Thank you. Thank you for that.
But take your seat, please. Thank you. 那么接下来我们将进行综合讲座。那么同步也要邀请我们现场的工作人员来协助的场地的布置。那么在正式开始之前呢，将要来收集现场所有贵宾朋友们的提问。那您也可以看一下我们的正上头，有请工作人员来秀出我们今天的 QR code。那么您可以扫描现场荧幕画面的 QR code， 就今天的主题水务行业的数位发展议题，表达您的看法以及疑问，也请大家把握一下时间哦。Before we proceed to the panel discussion, and we will take this opportunity to collect your question. We invite all audience members to scan the QR code on the screen and share your opinion or question. 那么接下来将进行专家座谈，今天的座谈主题是水务行业的数位发展。很荣幸再一次的来邀请到我们今天的主持人，有请到经济部水利署简志源主任秘书，以及国立成功大学水利及海洋工程学系董东吉系主任，有请。接下来我们也要邀请今天座谈的4位与谈人，分别为台湾自来水股份有限公司吴金文副总经理，以及国立台湾大学土木工程学系陈俊山特聘教授，有请。接下来邀请到的是荷兰戴尔夫特联合国教科文组 Professor Zora Vojanovic。最后，我们邀请到基士德科技股份有限公司卓国权技术总监，再一次有请各位上台就座，同时别忘了扫描您画面上头的 QR code 来进行线上的提问。Next, we will move on to a panel discussion. May we invite today's moderator and speaker to come up to the stage. We now invite all 6 discussants to the stage, and please give a warm round of applause to him, and please continue to scan the QR code on the screen to submit your question for the panel discussion. We now hand over the session to our moderator, Mr. Jian and Professor Dong.
Okay, thank you. All the experts here to provide excellent presentations, especially start from water supply to AI's application in engineering, as well as NBS, nature-based solution, as well as digital twin, and last but not least, about the smart water process, water treatment applications. So we have very good learning with regard to the watershed development and water governance. We have a very new solution and insights. Next, we have the last section. We will focus on so-called the Q&A discussions. So perhaps can we start from Mr. Jen, General Secretary, and to comment on the subject. Thank you very much. So all 4 speakers provide very insight comment. So now the floor is open for questions. First of all, Can I ask Mr. Wu that in your presentation you mentioned that your company utilizes AI to make some water leak surveillance or the risk management. I would like to ask you that. So in your company, Taiwan Water Company, what is your challenge? Is that technical aspect or management or administrative issues? On top of that, so quite a lot of supply facilities. You have collected some users' information with regard to the privacy and cyber securities. Does Taiwan Water Corporation have any measurements to protect the security of the information? Thank you very much, Mr. Jen. First of all, regarding AI to support leak checking. So in the beginning, our primary goal is to check the leaking. We hope to collect a big data. In the early days, so from the team, less than 100 people, maybe 80 or 90, these are the senior masters with a very long experience, but we need to cover such a huge territory. So our question is how to pass those experience of those senior masters and optimize them, and teach the young engineer to learn from their experience, and plus the support of AI. In the beginning, our challenge or major challenge is that our data is not big enough. That is to say, for those leakage, it is indeed a leakage, but we also need to collect the volume, the diameters of the pipes. In the beginning, we don't have a very comprehensive data. We just keep try and to collect the real world data, to collect more diversified information, so to make the database more comprehensive, to have a clear identification whether it's a delay or, for example, the plastic pipes, or at the moment we use PIP, or in early days we use PSCP or current HPP, different materials, different cost of the leakage. So in the beginning, the primary challenge is that the data is not very comprehensive. But now, once we have established enough data, during this project promotion, the identification rate is much better. So with regard to the labor part, actually we can train more staffs, but we need to keep the heritage of the senior masters. That's how we utilize AI to check water leakage. So next is regarding Mr. Jen mentioned about CI territory, how to utilize AI to have a best balance with cybersecurity. That's the focus of not only on the company, but the Ministry of Economic Affairs, including the central government. We also pay attention to the cybersecurity. We want to continue to use AI, but we don't want to see any gap, so the external people can break through or hack in. So that's one of the key points that we will work on. Thank you very much, Mr. Wu. So next question is to Professor Chen. So during your presentation, you talk about AI become a professional experts. I want to share my comments. So this is very relevant to the staff for the hydrologists. So I would like to ask Dr. Chen. So the application of AI in the hydrology and the engineering, on top of the screening or safety assessments, do you feel that are there any potential application with AI? That's my first question. Secondly, so since AI can help us, either the report or analysis or the inspection. It all relevant or related to the professional engineers. How to make sure that AI will not replace human beings in terms of the value aspect. So, in overall, I would like to deliver a message that AI is not just a simple model. AI is already an engineer. That's, you may say so. That as the Mr. Jess mentioned, where is the application? I mean, let me give you an analogy. So now you have hundreds of AI engineers. Maybe they are very junior. They just check or the literature search, and the question is what can a junior engineer do? So personally, I feel that 10 times productivity is necessary, it's mandatory. That's a minimum requirement. I think for a seasoned engineer, it will be a significant incentive, because in the past, young people can learn faster, but now the challenge for the younger is even more deep. They don't have time, opportunity to learn because of the AI pressure. So how to utilize these naive engineers? That's what I mean, to create something that we need to spend years to achieve. I mean, AI can help you to generate a report, but the decision making is even more important. Like the seasoned masters is less and less, getting less and less. So we really need to break through from this barrier, so we can. It's a take-home message is that now we have hundreds of free young engineers. So we have a lot to learn. So automation is just the beginning. So to support the decision, create the more value-added the objective. I think we can enjoy more about the AI application. So this is the foundation for that question. I think we have a great potential. That's the first one. The second question is that I suppose it will not change at all. So because human beings is engineer. AI is never an engineer, but how to search is a criteria. It requires all aspects. For example, if we want AI to read the hydrology, that is something we need to train AI. But in the end of the day, AI is just a support device. But in the end, the final decision-making and the responsibility is always on our shoulder in human beings. That is something I don't think it will change. I think in the future, it will remain the same. The responsibility and the decision is still on our shoulder. So the question is how to accurately make a decision to justify whether it is right or wrong. So that is very important. Thank you very much. So it sounds like the engineers still have the value, right? So thank you very much. So perhaps next two speakers, and next I would like to ask one question to Zoran regarding the MBS and digital twins. That is when you integrate the DBS and digital twins, what are the challenges?
Digital twins to enhance the watershed and urban resilience. So when implementing this hybrid resilience governance, what do you see as the greatest challenge? Is technical integration or cross-sector coordination, or even the social participants? And the second question is, how can we build more repeatable governance models in the future? Can you give us some of your ideas on that?
Thank you very much. I don't think this This is okay. Let's use yours. Yes, thank you very much for these interesting questions. I see a lot of challenges when it comes to the application of AI to boost the enhancement or to enhance the performance of nature-based solutions. Of course, there is a great deal of challenges for the nature-based solutions to be implemented in a way that we want to implement them, and we want to implement them to deal with multiple hazards, to reduce cascading effects, and to provide multiple benefits across the different areas. One is water management, looking to quantities, qualities, but also biodiversity and the societal use. So there already is a huge scope or a number of challenges there. But then when it comes to the use of digital technologies and AI, then of course there is a challenge there. Everything together is still very much on the shoulders of the experts from the domain knowledge. So we are still quite far from the more general use by the ordinary engineers from the water utilities. So it's still, there is still a demand for advancing the knowledge and to be competent in what you're using. So also, the way how we set up the AI models is not a trivial thing. It's very tricky in the sense, like if you're doing deep learning, if you have your input-output variables, how do you choose your variables? How do you set up your model? How do you define your parameters? So a lot is there. This is, of course, what we're doing right now is just the beginning of the journey. But there are a lot of challenges. Of course, there is, I mentioned in one of my closing slides that there is perhaps in the future that I'll see one of the grand challenges is how to connect these technologies on both sides with the communities, with the societies. And increasingly we are working more towards the transdisciplinary way of working, where we need to work with people from humanities and social science, which brings a different level. And that level is not only trying to deal with the minimizing, let's say, damages and optimizing functioning of a water system, but also how to make decisions that are the most ethical or the most, how to say, they bring social environmental justice. And this is something where the AI cannot play a role right now. And this is where we need a lot of human intervention. And then your second question was about the governance and how do we achieve more governance, how do we bring governance into the whole perspective of nature-based solutions and the AI and digital twins and things like that. Well, first we need to start with the capacity building, digital capacity building, but then there is also the important aspect of digital equity, I would say, and data sharing. And I think some of the previous speakers, they mentioned that the data sharing is very important. We are still, many organizations and water utilities, they remain closed when it comes to data sharing. So we need to establish the data sharing functionality, then the data standards and the model standards and everything else, and then we build a digital capacity so that it can become more how to say, applicable to the governance and to enhancing the governance in other structures. Yeah, yeah. Thank you.
So it looks we have still some road to walk, but we already on the way. So thank you, Lauren. And 我想对我们第四位做。
And now to our fourth speaker, Mr. Zhou, a few questions there. In your presentation, you talked about at your company, in your AI empowerment technology chain, there are several aspects. So in promoting smart water management, the greatest challenge you mentioned, is it on integrating the different data sets or building the AI models? Perhaps you can share your insights with us. Speaking of challenges, whether it is integrating data sets or the application of language models, with all the data we've collected and the scenarios where we want to apply them. With each application scenario, it is both are challenges. First of all, with the data we've collected, we can classify them us information that's diversified and from different data sets. So based on our old understanding, we may think I want to collect water flows, water quality, or environmental data. But then we also find when we apply AI and especially feature engineering, when we want to extract the features, we find that with these data and the AI output we are able to generate, they are unrelated. And when we do the Pearson analysis, the correlation coefficient is very low. So in my work, mainly we need to manage the deployment of sensors rather than integrating the data sets. So the question is whether it's a watershed or a treatment system, sewage treatment system, or a water supply system. How do we deploy the sensors? Which sensor do we need to deploy? And the results using these sensors to monitor, they need to be relevant to the AI output. So this is one of the greater challenges I ran into. First, with these, is there enough density for your sensor deployment? And second, what you are collecting with your sensor, can you use it to inform AI and enable machine learning? So does it have high relevance to my output? So with the first thing I've done is to help them deploy the sensors and to put them in the right place, and then to communicate and coordinate with the competent authorities. There is also another key problem. With these sensors and the data they collect, is it accurate enough? That's also another issue. As we develop AI, that's a headache for us. Often with sensors, the location you place it is incorrect, or there is a blind spot, and it's not fully applicable. So there may be molding, there may be structural issues. So all these compromise the AI output. Thank you for that. We have a little time left. Shall we open the floor for some questions? Secretary General, would you like to pick a few questions for us? Sure. Thank you. Thank you to the audience for questions. Actually, I don't know which questions to raise. Maybe I will go to Mr. Wu first. You talked about using voice identification to identify the leaks. And in terms of system engineering, what about the pipework flow and pressure measurement to identify leaks? Is that a way to go forward? Thank you, Secretary General, for this question. The key here is, in addition to using AI to identify leaks, as you said, we can use our pipe network to confirm and discover suspicious leaks. So basically, we mainly rely on our WADA system, which has a district or area-based concept. So if we have a comprehensive design for a district, we can look at how much is coming in, the input versus the output. And whether it is in the input or output, we look at the flow. And in the district, we may have pressure measurement. So using the WADA system, we have long-term data on this area, maybe historical data over years, to see the water use conditions and stats, the pressure stats, to predict whether or not there is anomalies during a certain period of time compared to history. So these are suspicious spots, and when there is delta, then we deploy people onto the field. Maybe it's the monitoring equipment, or maybe because of water supply, where they adjust the valves, or maybe there are some variables that require field checks. So usually with the area-based pipework, this is how we review them. Thank you for that response. So you use flow, pressure, all these variables, but you need sufficient measuring equipment to ensure that you have information on this area and then expanding it to the entire system. If time allows, may I ask one more question to Professor Chen? Question from the floor. Professor Chen, using AI to save daily tasks for the engineer and passing on experience, how do you ensure the passing of information and automation? What's your this is a very big question. There is a benchmark that you can use, and you can go to Sinotech, which is with whom we have a lot of ongoing research projects, with a lot of our AI projects. At the school, we look at points and look at the feasibility, but in terms of implementation, and there are so many things to do. There is cybersecurity, intelligence, incentives. All these are complex issues. You cannot just rely on a few AI technologies to enable that. So in the engineering sector, we are working hard, and this is the golden time. So we are all starting, and it's like a race. We need to see who can move the fastest. So this is a great cross point. All the intelligence, the AI, we are now ready to deploy them. So feasibility study is definitely necessary, and you can work very closely with schools. We have a lot of professors here. Feasibility to see if all the basics are in place, how much the budgeting. These are easy, but implementation, we definitely need a company or an organization to take the initiative. So don't expect the professors to help you implement. They can't do that. They are very good at standing on the sideline and watching, just joking. So I think this is the best way we can collaborate between the academia and the industry and take advantage of this great opportunity. Academia can provide feasibility recommendation and implementation. We need the private sector to do it. Actually, Sinotech is in the audience, so you can discuss with them on the practicalities. And back to the moderator.
For Roland. So in some areas, some countries, that the policy implement tend to be short-term. So can you share your experience in the Netherlands, how to promoting or implementation the long-term MES policy? Can you give me some comments?
Yeah, thank you very much. So the question is between the short-term policy and the long-term policy, yes, and nature-based solutions. Obviously, dealing with nature-based solutions, particularly on the large scale, such as the measures that follow in the, let's say, room for the river type of application. So these are the measures that occupy large spaces, large areas. So in terms of the policy in the Netherlands, it is very much driven with the land development and also nature protection. So there are many areas in the Netherlands which are protected, that you really cannot do anything with those areas. There is also EU obligation towards the Nature 2000 law and policy, which means that that certain areas cannot be touched. So what the Dutch have done, what's been done in the Netherlands in that context is that as long as you can prove that you can actually enhance that area where you're implementing nature-based solutions or any kind of interventions,
you are enhancing the nature aspects through the assessment of the biodiversity, species, and all other environmental studies, you are basically not allowed to touch that area. So introducing a policy which can be very much impact-driven and also not only minimizing the impacts, but actually dealing with the land development in a way that you can actually enhance these benefits, then it can work. So putting the policies and other regulatory frameworks in that area to sort of channel the developments to be in that direction can help a lot. That's in the Netherlands. Also, the building development codes are very important, particularly dealing with the flood-prone areas. The policy in terms of the if you live just immediately behind the dike or area which is where the nature-based solutions have been implemented, you have one set of design guidelines that you need to achieve, and then if you live a little bit further out, then you have another set of design guidelines. So implementing these kind of policies that can drive the not only land development and nature protection, but also development codes on the buildings. So that's played an important role in the Netherlands on the long run, how to cope. Yes.
Sure. Thank you. So thank you for sharing your experience for us. 因为时间关系，我们就
In the interest of time, we will entertain one last question from the floor. This is a question about wastewater treatment and smart technology, and one difficulty that this person ran into, the frontline staff. What do they think? Is there any resistance, or is there any support from the executives, from the management? I will use my own company as an example. For the wastewater treatment plants and the workers there, to be honest with you, they try to minimize the work they have to do. You tell them about AI and how much labor they can save. Actually, they think it's a burden and pressure for them. However, to the company has to do it. It's necessity, especially for the management. First of all, energy and carbon reduction goals necessitate this direction. Also, this is a corporate strategic direction because it involves ESG and their commitments. So in the implementation, of course, communication and coordination are pivotal, and you need to do a lot of education. And we are no exception. This is how we do it. This morning, during the summit, Director General Lin mentioned that there are some basic principles and concepts and knowledge and some basic technologies. We need to improve education across those areas to ensure that everyone is moving toward the same direction toward smart watershed and a smart water sector. Based on my past experience over the years promoting smart wastewater treatment operation, we start with the operators and the managers. We inform them that AI is not here to replace you, to replace your work or your tasks. It's to help you better understand how you can leverage AI to solve problems and how to enhance and add value using AI. So we're trying to educate this to help with our ESG commitments and our own AI enabling capacity. This is how we communicate with everyone inside the company, especially the base level workers. Thank you for that. In the interest of time, I will draw a few conclusive remarks. First of all, I want to thank the 4 speakers who have contributed to information and digital development in the water sector. This forum is teaching us how and helping us to make our water sector smarter and better AI-driven, embracing a new sustainable age, bringing governance and technology together to help us better manage and become more efficient, transparent, and resilient. I want to thank all of you for joining this session. Thank you for your participation. And we are together witnessing the water sector moving toward a smarter and more sustainable future. And with that, I'd like to conclude this session. Thank you all, ladies and gentlemen, for your participation. I wish you health and prosperity.
谢谢今天的主持人，谢谢简主秘、董主任、伍副总，以及我们现场的陈教授 Professor Vujanovic， 以及我们的周总监，再一次的谢谢。非常感谢。那么这边呢，也要再一次感谢现场所有贵宾的与会。今天的论坛到此完美落幕。会后大家也可以利用简短的时间互相交流，为水务行业出谋划策。我们下次再见。Thank you all for attending today's forum. We invite everyone to take this opportunity to network and exchange ideas for further advance the water industry. Once again, thank you for your participation. See you next time.